Hello, welcome. I have to share with you, this is tremendously frustrating. This is the third time I'm recording this. Um, just the technology, I suppose. So, let's see if it works now. Um, we're going to discuss what we've been talking in class about model selection. In particular, we've been focused last week, well, this week really, on resampling techniques. And since this is a biostatistics course, I think it's appropriate to dive a little bit deeper into this topic because we're we're moving in the direction of incredible technology, and as that, keeps going, our data sets are becoming bigger and bigger and bigger. We really are plagued with this curse of dimensionality constantly, and that may in fact be true in other fields as well. I imagine that it is. So we have to give a little bit of attention into how to do model selection the right way when we have a severely underdetermined problem. So we have far fewer samples as we do, let's say, traits on a microarray. So we're going to talk today about a paper that was published in PNAS. And this paper is a really nice paper. First of all, PNAS is the Proceedings of the National Academy of Sciences. Is a very high impact journal, and so it has an impact factor of about 10. It's rare for a statistics paper to be featured in this journal. Typically, this is a more, let's say, you have to have some data to go with it. It's usually not enough to do some secondary analysis to get into PNAS. But this paper was seen as so important because I think these methods are being applied in the wrong way, and these models are overly optimistic, and if you hand somebody a model that's overly optimistic and they waste a lot of resources trying to follow that model and its predictions, you're going to waste a lot of time and money that way. So we have to be very cautious about, once we build our models, we have to make sure with utmost confidence and statistical assurance that we have the very best model and we did things in the most appropriate way. Now, microarrays pose a particularly challenging problem because their dimensionality is so severe that there's inevitably some feature selection that has to take place. So the question then becomes how to do feature selection appropriately when you're doing this cross-validation or bootstrapping scheme to estimate prediction error. And the answer to that question is also in this paper, but it was in our text, and that is particular, you have to implement these resampling techniques at the very beginning of the gene selection process. Otherwise, you're introducing a great deal of bias, and your estimated prediction error could actually look almost as good as a training error, which should look really suspicious to you, especially in huge problems. So this is the goal of this paper, and these guys are from a math department. They found several examples of these botched analyses, and they kind of call them out on it. And but what's most useful in this paper is that they show if you do the analyses the right way, this is what you can expect to see. This is the right way for doing them, and here's the wrong way. And look at how optimistic this is. And so I think it's very useful. So incidentally, this is what you would call a journal club, and what I'm hoping we'll do at the end of the semester. So I, being the presenter, will select a paper that's relevant to what we're thinking about, and the class will read the paper. I will do a presentation which basically goes through the paper and the methods, and then we discuss it. Of course, we're lacking the discussion aspect of it, but that's the main idea. So that's what I'm basically going to do. I'm going to run this like I would a journal club. I'm going to go through the paper, and and I'm not going to go through, section by section. I need to introduce a little bit of background, and that's kind of what you'll have to do as well. You'll have to give a background into the technology or into the problem itself, and so you might have to do some additional digging. So what I'm going to do for my background is I'm going to recap selection bias in the text, and we saw this in a smaller example. I'm going to talk about microarrays, the technology that is under investigation. I'm going to talk about what the authors did that was so wrong. And incidentally, they did exactly what we talked about in the text, only it was much more severe. Cross-validation and the bootstrap. Now, we've talked about these methods, but I always say it's good to see things more than once. Sometimes you see things in a different way and you're like, oh, I understand. And so we're going to go through their presentation of cross-validation and bootstrap. Then we're going to look at colon and leukemia gene expression data. These are two very famous data sets that are still used today. And then finally we'll wrap up with some conclusions. So let's get started. Consider the following experiment. You have a massive number of predictors and a small sample size. Incidentally, in a standard classification problem, you usually have an n that is much greater than p. So that's a great situation to be in. Now we're faced with a situation, almost always, in bioinformatics and biostatistics that looks like this. N is severely less than p. This is an underdetermined problem. And the problems that we're considering, we want to build models. So it's not only an underdetermined problem, it's an underdetermined inverse problem. An inverse problem is when you have an output and you want to unveil the input, which in this case is the model. So this is particularly challenging. Here's the wrong approach for doing so. The wrong approach is to screen the predictors based on Y. So if you screen a predictor and then you find a subset of good predictors that show a strong univariate correlation with class labels. So now you've messed up because you used the whole sample and you're looking for univariate correlation with the class labels. So you're biasing your solution. Then you're going to go on and use just that subset of predictors to build a multivariate classifier. Then use cross-validation to estimate the unknown tuning parameters and to estimate the prediction error of the final model. Okay, there's many blunders here. First of all, the predictors were chosen in step 1 on the basis of all the samples. Okay, so first thing is that in underdetermined problems, especially microarrays, there's always going to be a feature selection stage before the model building begins. Okay, so by feature selection, we mean we have to filter the data in such a way that we can actually compute something. And so that's inevitable. We can appreciate that. You can do that, but you can't take into consideration all of the samples and then look at the correlation with the class labels. That's two bad things. Then you're going to bring in cross-validation, but it's too little too late. You're dicing up the data after the fact, and the test data has already been seen by the classifier. So anything you come up with prediction error is totally off. So here, if you have a true error rate of 50%, so although I erased it here, our input was totally independent of the output, so you'd expect to see nothing. And by nothing, we mean an error rate of 50%. And you come out with a predicted error of 3%. Okay, so that's pretty bad. So you have a model that's total garbage, and it looks really good. So that's like that garbage in, garbage out idea that we talked about at the very beginning of the semester. So that model wouldn't generalize well. And the right way to do it would be to bring in the cross-validation at the very beginning. You have to consider it when you do the feature selection. It must be applied to the entire sequence of modeling steps. Samples must be left out before any filtering can be done. It's okay to filter on something that does not involve Y, for example, unsupervised techniques or variants, or univariate t-tests. So unsupervised techniques might include something like clustering or a graphical model. But even those are difficult, I think. Doing feature selection based on clustering is a little bit, yeah. So you are going to introduce some bias by doing this, but certainly not as much as you would if you were to involve Y in that process. So this is a major problem in the literature, and so we're going to explore a few different data sets in which that was done. So this is the paper we're talking about today. Now, here I say they attack prediction rules for small number of samples, which are subject to selection bias. Attacking might be a strong word. They discuss it, and they say why it's wrong, and they take two data sets and they apply an equivalent of the methods that were applied by the authors in the wrong way, and they see this overly optimistic test error prediction, and then they apply them in the way that they should have been applied, and they see what the true error rate would be, which was much higher. Excuse me, I can't believe I'm so sick. So they focused on a recent paper where the authors claim a predictor, actually they focused on a couple papers. They claim a predictor based on a few genes for tumor classification with a negligible prediction error rate. And so, okay, let's talk about microarray technology because that's what we're going to be dealing with. This is a microarray. There's all of these little dots, or this is an Affy array. All of these dots stand for different transcripts, and the colors are their signal once the DNA hybridizes to them. And so, usually, a microarray has between 10 and 100 samples, but as technology increases and improves, the number of assays goes up. So, for example, in 2002, we were dealing with microarrays between 2,000 and 6,000. Those are the ones considered in this paper. Now we're seeing 40,000 transcripts on a regular microarray. And this number of samples is not really increasing to, you'd have to increase it through the roof in order for it to match. It wouldn't be even possible. But even in studies like GWAS studies where you might have, 500 to a couple thousand in the most comprehensive GWAS studies, you run into a problem. So you have a mismatch here, the samples and transcripts. This is severely underdetermined. And now you might say, well, wait, I thought we were looking at genes and this is confusing. Okay, well, first of all, you can see that you can't fit a model from 40,000 transcripts. You're going to have to do some kind of feature selection. So what does a transcript mean? A transcript is a representation of the gene. So it is, a gene has a length here. It's on some chromosome. It's got some length. And, maybe a transcript, one of the transcripts is from, X megabases to Y megabases. And, another transcript is from, Z to W. And so you have many different transcripts, sometimes as many as, 5 different transcripts for a single gene. And they're really just different measures, a different set of probes that summarizes that gene's activity. So in the human genome, there's there's 20,000 or 22,000 genes. And so as a first feature selection problem that we face is to go from the transcript to the gene level. And so that's challenging in itself. So that's typically done in the ways that I discussed, where you look at some univariate result like a t-test, or you look at the transcript with the highest variance. And typically these transcripts mirror each other because they're really just regions of the same, different regions of that gene. Many of them are overlapping, but there are situations where, there might be one that doesn't hybridize correctly. There's a broken spot on the array. And so, you could throw that out. Okay. So let's talk about what makes this problem particularly hard. First of all, you have the severely underdetermined problem as we discussed. Selection tasks are difficult, if not impossible, on 40,000 transcripts. You just can't do it. You can't consider all of them. We have to do feature selection. And with a limited number of samples, we can't really afford to set anything aside for a test and validation set, so that's why we want to use these resampling methods. In general, these techniques are prone to selection bias. So here's some background into the problem. This is really what's going on everywhere in biology. There's an emphasis on shifting paradigms from morphologic to molecular in an effort to uncover mechanism. In particular, morphologic really pertains to structure, structural properties. Molecular focuses more on function. So we really want to uncover mechanism. And that really speaks to, this idea of personalized medicine and so forth. We want to be able to construct models such that when we change the input a little bit, we can predict an output response. In the case at hand, we're looking at gene expression. If, somebody has, if you have 3 genes in the classifier, which, is ridiculous in itself, but, and you have these expressions for this, for these 3 genes, you should be able to predict if you have a malignant or benign tumor for a particular tissue. So that's an example of what the trends are becoming in biology. And the problem that we're facing then is to construct a classifier or a prediction rule, R, that can accurately predict the class of origin of tumor tissue with a feature vector X, which is unclassified with respect to tissue type G. Okay, that's a pretty tall order. You can imagine that if you saw that classification task and you saw the size of the data set, in particular the curse of dimensionality, and you saw a 3% error rate, you would be a little bit suspicious. And that's the way you should kind of view these papers. The data is microarray. Each tissue is assayed using microarray technology. So if you were to think about a microarray data set, the hardcore data, you have essentially a matrix where you have all of the genes in the rows, and then you have each sample being the columns. So what makes this problem particularly challenging? There's a number of reasons. We said that, first of all, in classical standard discriminant analysis, we usually have a situation. I mean, these methods were written for situations where we have a well-determined system, n is greater than p, or even more ideally, n is really greater than p. And in our case, the prediction rule will not be able to be formed from all of the genes. It's just impossible. Computationally and adding all of that noise to the problem will cause big issues. If it is possible to include all genes, doing so will add considerable noise. I just said that. The generalization error, test error, will increase with the number of genes considered in the model. So for that reason, feature selection is inevitable. Okay, so I think we've nailed that point. So there's 2 approaches to feature selection that they discuss. A filter approach is just an approach that establishes a criterion that is independent of the prediction rule. In a wrapper approach, the criterion depends on the rule. And rule assessment, leave one out cross-validation, can be used to assess the performance of the rule. Note that if this is calculated within the feature selection process, the estimated prediction error is prone to selection bias. To correct properly, CV or bootstrap should be carried out after feature selection. So what did the authors do that was so wrong? This is the example. This is one example for 3 data sets. The authors report an LDA rule formed with only 2 to 3 genes through forward selection, which we know is kind of a crude algorithm anyways. And they say that that can achieve 90% or better accuracy for classification. And the flow is like this. The feature selection process was carried out on all of the samples. Following that, the data was divided into a training set and a test set. The rule was then trained on S1 and tested on S2. Okay, so it was trained on the training set and tested on the test set. This was done over 200 random divisions, S1 and S2, and the results were averaged. So what's the problem here? The feature selection process was carried out on all of the samples. Okay? Following that, the data was divided into 2 sets, and then the rule was trained. This was done on 200 divisions. The problem is S2 is a subset of S. So essentially, the test data has seen the training data already. And this is going to drive the error to be too optimistic. Here's another example. Zhang et al. Constructed a classification tree, which we're going to talk about next week. Based on 3 genes for colon data, the error rate is 2% using local validation. The problem is there's 2,000 genes total, and again, S2 is a subset of S. So the test set has already seen the training data. The test error is too optimistic. Now, another method, another paper, Guyan et al. Used support vector machine on a leukemia dataset, and they claim a 0 error rate based on cross-validation. Again, it's this issue of the training data and the test data overlap, essentially. The test error is too optimistic. So we're going to talk about support vector machines, later in the semester, but we're going to talk about CART models as well. So you don't really have to have an understanding of the different supervised methods that are being used to appreciate the issues at hand. So how do we go ahead and correct for selection bias? So the motivation is that the CV error of the prediction rule obtained during the selection of genes will be too optimistic in estimating the error rate for a classifier R. To correct for this, it's critical that CV or the bootstrap be used external to the gene selection process. A popular method of doing this testing is to split the data into test and training. However, the tissue samples in the test set can't be used to form R. So we have to put those aside. This means R has to be formed with a reduced set of tissue samples, and usually we don't have a lot to begin with. In practice, we want to make full use of the data. So they talk about cross-validation, and so we're going to go through that again. M-fold cross-validation, they call it. We're calling it K-fold. The data is divided up into M non-overlapping subsets of roughly equal size, and the rule is trained on each of the M-1 subsets and applied to the remaining subset test set to estimate prediction error. Then you take the average for each one of those that it is applied to. You take an average, In the case of m is equal to n, we're in the most severe case, or it's a special case, of leave one out cross-validation. This is an unbiased, fairly unbiased estimate, but it's highly variable due to the fact that the training sets are so similar. In the case of feature selection from the full training set, the same feature selection rule has been implemented over the m-1 subsets, combined at each stage for gene selection. So if you want to do gene selection then, or feature selection from the full training set, you have to use the same rule, has to be implemented over the m-1 subsets and combined at each stage for gene selection. And the bootstrap. They're calling it bootstrap smoothing. You have bootstrap smoothing or leave one out cross-validation is given by the leave one out bootstrap error B1, which is exactly what we called it. That predicts the error at a point xj only from the bootstrap samples that do not contain the point xj. We were using that CJ notation. So suppose that k bootstrap samples of size n are obtained via resampling with replacement from the original data set of n classified tissue samples. Then r star k is the bootstrap version of the rule formed by the kth bootstrap sample in exactly the same way that r was formed from the original training set. Okay? Using the same exact gene selection procedure. So you're bringing it in right at the beginning. Now, they call this a Monte Carlo estimate of B1 on the basis of the kth bootstrap sample is given as follows, where E, yes, I didn't really like their formulation here. I didn't quite understand the meaning of Q. I is an indicator if xj is not contained in the kth bootstrap sample and 0 otherwise. That's fine. The Q being 1 if r misallocates xj and 0 otherwise. I wasn't quite seeing that. Nonetheless, we know that this bootstrap sample can be upwardly biased and overestimate the prediction error. So we know we can do better, and so they build up to it the same way we did. The 0.632 estimator will correct the bias of B1 by pushing it toward the training error, and the training error being AE, although I couldn't see where they defined AE. I'm assuming that they mean AE is the training error. So that's going to step us in the right direction for correcting the bias. But when you have situations of overfitting, the 0.632 plus is more appropriate, and that actually weights. B.632 plus is a weighting of the training error and the B1 estimate, where the weight is given by this ratio here, where this R is simply the difference between the B1 error estimate and the training error, and gamma and the training error, and gamma is the no information rate. Okay, so it's the same idea. In the example at hand, we have gamma is equal to the sum. This is the P proportion of the original tissue sample from the ith class. This is the proportion of them assigned to the ith class via R. Okay, so those are the two methods that we discussed in class, and in a slightly different way. But I think the bootstrap is at least straightforward. The CV as well. Now, the two data sets they look at are really classic. There are two AFI data sets. AFI is the name of the company that makes the microarray chip. Colon data of 62 samples, 40 tumors, and 22 normal tissues. Yeah, it's also rare to have this perfect divide. We've been doing equally split dichotomous outcomes, and so this is rare. So we have more disease than we do normal controls, and we have 2,000 genes. In the leukemia data set, we have 72 samples, and 47 cases of acute lymphoblastic leukemia, and 25 cases of acute myeloid leukemia. So no normal tissue there. We're looking at two different types of leukemia. And the number of genes is, the number of transcripts is 7,129. Actually, this might be genes, I'm not sure. So the first thing, their method that they use is backwards elimination with support vector machine. Rather than talk about that, the details aren't given, and we're going to do SVM in class, but we may not do backward elimination. But regardless, we can appreciate the results, so we're going to just keep going with that. And that's normal. You might, in a paper, you're not going to understand everything, and some things you'll know that you can just, skim over and so forth, and so that just takes practice. So here's some notation. This CV1 IE, leave one out, internal error. This is not correct for selection bias, okay? This is equivalent, they say in the paper, almost equivalent to what the authors were doing, that they're in fact slightly criticizing. So this is going to provide a pretty poor estimate. CV10E. This is the cross-validated tenfold error attained by an external cross-validation that does correct for selection bias. So this is cross-validation done in the correct way. And then you have the B.632 plus. This was formed using 30 bootstrap replications for each of the 50 splits for the full training set. This is also done correctly. So let's take a look at the results. I have them, I just copied them right from the paper and I put them side by side. The left one here, I believe, is the colon data. And here is the leukemia data set. And so then you have the error rate and you have log to the number of genes. So this is then 2 to the 6 genes and so forth. So you have to make that transformation. Now, let's take a look at what's going on. The biggest thing to realize, let's just look between data sets first. One is that the error rate, and then they have this test error, which I believe they just did a bunch of leave it out methods and average them together to approximate this. I'm not sure how they come to the true test error. I believe that's what they do. But nonetheless, they have a test error here, and that test error corresponds better to the cross-validation, tenfold cross-validation, and the bootstrap, of course. And then you see the training error, AE, way down here. You see that the CV, the leave one out cross-validation error that does not account for selection bias takes a dive as well, and it looks a lot like the training error, which is really what we would, what we were saying before. We would expect to see something like that. And now if we were having a discussion, we would be talking about, well, what happens here? I'm not really sure what happens here. It just jumps up. I'm not really sure why. And it seems to hit up with the test error. So that's one thing. And actually, you can see that if you were to rely on this this method that is wrong, you would come out with a model that takes a minimum probably right here at 2 to the 4 genes and 2 to the 4 genes for that model as well. And then you see the true error rate. Let's look at this is the colon data. Okay, so here you can see in general that this error is higher than the leukemia data, which means that probably the leukemia data set was easier to separate in general. We have, at least we have both the bootstrap and the tenfold cross-validations, at least in the standard error bounds. The bootstrap seems to be a little bit biased in this case. And they do a little bit of discussion upon why. And the CV, the tenfold cross-validation seems to do a little bit better, but there still is some bias here. And this is the model that you would come out with for this one. And then we have over here, these are a little bit more on track, the CV and the bootstraps seem to do reasonably well. They do a better job approximating the test error curve, which is probably more. So that is probably more of a consequence of the fact that these classes are easily separated, or at least easier separated than this. So we kind of get a feeling that, for this one, at least the bootstrap is more biased than the tenfold cross-validation error. Can we say that as a rule of thumb? Not really. This is one particular data set. That's why I want to look at that other paper, which looks at comparison of methods for this type of data and puts them to the test in that way. So, yeah, we can't draw any real conclusions about that from this data. So, let's see. The next thing that they do is a forward selection. And here we see the same type of thing. We have the AE being the test error, and this is for the colon data and the leukemia data again. In the forward selection case, and in both situations, again, we see this difference in error because of the complexity of the colon data, although it doesn't seem to be as severe as what was done with the support vector machine. So, for forward selection, we see that the training error and the leave one out error that doesn't account for selection bias pretty much track each other exactly for both data sets. So that's interesting. And they're also unreasonably low. So just like, well, we would expect the training error to dive to 0. And here it does, in fact, for the leukemia data set. But really, you would take a model somewhere over here for the minimum. And you might actually get the same model here. I'm not sure what the minimum would be, depending on which method you use. In this case, they don't have an estimate of the test error, so we have the bootstrap being the light gray, and then the dotted being the cross-validated tenfold error. And it looks like if you were to use that, you'd take a model out here, but for the bootstrap, maybe you'd be out here. So, but anyways, it would be ridiculously bigger than it would here. And that's for the colon data. And for the leukemia data, now we see something interesting because they seem to be pretty much on track with each other for the SVM, but here they're changing quite a bit. We see that diving to 0, but here we see the cross-validated tenfold error choosing a model over here, and then the bootstrap would be way out here. They're not really agreeing on the same model, which is a little bit concerning. So we'd have very different results for that one. But the message being that whichever one you choose, the curves are way different than if you were to not correct for selection bias. So now it's interesting to see. The next questions are, well, what's going on here? You'd pick two very different models. Which method should you use? I don't know that answer. Maybe you should use both methods. So this is the kind of thing we would want to do in a discussion. And maybe we'll get some insight from the next paper. Now they do something really neat. So what if there's no information in the data set? You can do that easily by permuting the class labels randomly. So there should be essentially no correspondence. So they did this 20 times. They created 20 data sets, and they fit the SVM rule to the model. And what they found was what you would expect. The training error dives down to 0, as it always would. And then this leave one out cross-validation that doesn't allow for selection bias also dives down with the training error, although not tracking it exactly. It's telling us that, wow, this is a great model with 3% error. You would pick a model probably right here, where realistically there's absolutely no information in the data set from which you could derive any conclusion or any model. And so, rightly so, I'm not sure what gamma is here. Oh, that's the no information rate. Okay. So the bootstrap and the cross-validated tenfold error pretty much track each other with the no information rate. They are between, I'd say, 45 and 50% where they should be. Okay. And they should also be pretty steady across the set. So that's really a powerful message. I think that this is the most powerful message of the paper. Here you have no information, and you can fit a model that tells you that the test error rate is fantastic. That's a real problem, and I think that this picture kind of drives the message home, at least in my eyes. In particular, because it's not dependent on any the method and the data set. It's essentially a simulation. So here are some conclusions that the authors present. Essentially what they've done is they've demonstrated the importance of correcting for selection bias and prediction error estimation, formed by using a subset of genes selected from a large number of genes. And they've certainly demonstrated that with 2 data sets and a number of different techniques, along with a simulated data set. Then, if the test set is used to estimate prediction error, then there will be selection bias. If this set was used for gene selection. Okay, so that was the travesty that occurred in the other papers. The test set must play no role in the gene selection process. It's not practical to put observations aside, but we can implement the bootstrap and CV as described earlier. So now we have kind of a framework for doing so, and we understand the consequences that go with not implementing it properly. So, what do we want to take away from this? I really think that this image is the driving point, and just as we move forward in our own research paths, as we read papers and are presented different models, we should be a little bit suspicious because it's not exactly straightforward how to do the feature selection that's required, and how to ensure that the results are not biased. And as the problems become more and more complex, it becomes a little bit hazier in how to do so. So thank you. This is how I would do a journal club. So if you're thinking about your final project, this is the idea. And so in the next segment we will talk about a comparison of methods. Thank you.